My name is Bob Amar. I'm an independent school teacher in the Atlanta, Georgia metro area, and I am most pleased to be with you tonight talking about calculus. So let's go ahead and do the usuals. I see they have added a TikTok to the Think Fiveable slide. I have not noticed that before, so there it is. It has all the usual stuff though. Instagram, Twitter. Give us a follow on one of those. I have no idea what's on the Think Fiveable TikTok. I'm very curious to see. YouTube. We got some of the stuff is on YouTube as well. So, all right. So let's dig in a little bit. If you have been some of our recent streams, Mr. I went over the graph of a derivative, what it does, how to use a derivative function in various contexts. So we're going to really extend that tonight. I'm going to try to get you hit the ground running here, but if you're sitting here and you're like, wow, this is kind of like wow, then we have some other stuff that predates this as well. So I hope that you will go back and take a look at that as well. I have some cautions about using this graph. I have a couple of different traps that I see students fall into when they answer questions like these. And so I want to alert you to them. And then we're just going to work some free response questions. I may go over the 60. So actually, I really want to work all the examples I have tonight. So let's go ahead and get started. I always like to start with a warm-up. And in this warm-up, I'm giving you the graph of a derivative. So the function graphed in red is a derivative, okay? It's the derivative of the function f. And I would like to ask you some questions about f, okay? So this is f of x is defined for all real numbers, but I'm just asking you to make judgments on 0 through 8. So I really, really want you to go ahead and grab a look at these 5 questions. I think I am in the way of the number 5 at the bottom, but I think you can do this. They're kind of like, this is kind of like a tier list of different things, except I guess it's upside down if it's a tier list. So go ahead and take a look at these questions. In order to prevent there from being like super uncomfortable silence while you work this, I am going to let you have some silence because I think it's important. But in a few seconds, I'm going to talk you through a couple of different things that I see in this warm-up. Okay, so we will take about a minute here, just looking, and then we'll see where we want to go from there. Take about maybe about another 15 seconds. All right. So here are some thoughts that I have as I think through this. I'm looking at a graph of f prime. I want to think about f prime's graph as sort of a really sophisticated table for f. So if I look at the value, if I look at the graph and I see that there is a value for f prime, I'm going to use it. Okay, so that's one aspect of this. The other thing is that remember that there's a certain level of depth to the way we think about functions in calculus. A function can there are 2 layers of derivatives that a function has that are useful to us when we analyze functions. So the first layer tells us about increasing and decreasing behavior. So if I have the function f and I have its first derivative, that tells me something about its increasing and decreasing behavior. From that behavior, I can actually infer other things about it. The second derivative tells us about how besides being how fast the first derivative is going through its own changes. The second derivative tells us something about the shape of a graph. So if a function is twice differentiable, that's a fancy way of saying its second derivative exists, then we know things about what its graph should look like. A function has a positive second derivative, then at that point it's going to where we evaluate that is going to be part of a concave up or concave down section. And a point of inflection is where a function changes from being concave up to concave down, assuming that it happens at a single point, which is in the domain of the function. Okay. All right, I think I've talked for long enough. Feel free to, we're going to go, let's just hit these questions one by one. And I'm going to switch over to my notebook here. So in the meantime, go ahead and pop some answers in for question number 1. This is, we're going to get out the big guns here. Okay, not differentiable at 2 and 4, not differentiable at 2. Okay, so not a 2, not a 4. Okay. All right. All right. That's too far down there. Okay. So let me get my screen size right, because I know that that's a problem. Thank you. I was like, when else am I going to wear this? We got them for Pi Day last year, and I just keep getting mileage out of this shirt. So I haven't checked whether the math is like all right on here. Some of it is just symbols put together, but some of it's interesting. I don't know, but we can talk about that later. Okay, so I've got lots of questions about, or I got lots of answers about x equals 2. That's okay. So let me double check, make sure I'm doing the right thing there. Okay, so I got lots of things about x equals 2, and I certainly see that. So let me just start writing some answers down here. So for part 1, x equals 2, since f prime of 2 is undefined, right? It has a hole. Has a hole at x equals 2. A lot of people are saying x equals 4. And I have a question. If I asked you to look at this graph and tell me what f prime of 4 was, what would you tell me it was? Let me move the chat over so I can see it. All right, there we go. Huh. Okay. Interesting. This is interesting. Okay, so I will tell you what I intended, and then you can tell me what you think of that. But I intended for this graph to be defined at 4, -3. Nikki, there are if you go to the event, I think in the down below there should be a link to the slides. I didn't make a PDF of them, but the slides are Google Slides. So hopefully, if you can see this presentation, you should be able to see. You should be able to see those slides as well. Okay. So this is one of my things that people get fooled by this all the time. F prime of 4 equals -3. So f is differentiable at 4. F is differentiable at x equals 4. What's not differentiable is f prime. But I wasn't asking you about f prime. I was asking you about f. And that's a key distinction. The AP folks are going to definitely want to know whether you can tell the difference between that or not. Okay, so it is the case that f prime is differentiable, not differentiable. But we're not talking about f prime, are we? when I'm teaching and I do something kind of tricky, I like to put a little fangy face there, so you know that I'm okay. So what does the graph look like? I saw a couple answers. Okay, somebody asked, can I explain that more? Let me hit what the graph looks like, then I'll go back, and Melody, I'd like to get your question on can I explain that more, and I'd like to know what that is. I'm not putting you on blast. I just want to know what I just want to know what I can explain a little more. I'll try, even if you're not sure. Okay, a couple of people answered, and I think I saw most of you agreeing that it would be a cusp. Some of you said it would be an asymptote. The derivative is a number heading into each of these things. The derivative doesn't go to infinity, so I would not expect there to be an asymptote. This looks to me like there will be a cusp at x equals 2, or f has a cusp at x equals 2. I would not expect that to be an asymptote, even though the function's not defined there. F double prime of 4 does not exist. That's right, does not exist because of the cusp. So f double prime of 4 doesn't exist, but f prime of 4 is -3. Okay. So that's an important thing. I think a lot of people get tricked by that. I've seen like lots of multiple choice questions like that, but I wouldn't put it past them to ask a question like that in free response form as well. A cusp, we think about cusps. That's a great question. So let's talk about that just for a second. Okay, so real quick, a cusp is when there is a maybe that's a corner then. That might be a corner. That's what I was just going to tell you. Technically, what we do, it looks like a cusp. But technically, a cusp has a vertical tangent. It looks like a seagull. And a corner does not have a vertical tangent. So I guess I dropped my pen. That's awesome. Okay, okay, yeah. So a corner, this would actually be, I'm sorry. Yeah, you're right. Thank you. I'd expect this to be a corner at x equals 2. If the derivative is increasing, I expect it to be a parabola, and then kind of like cornered with a cubic coming off of it. Yeah, I will. Yeah, let me grab a couple different things. Let's see. Let me pull up a textbook. Okay, so while we're doing that, so f is differentiable except at x equals 2. The graph clearly shows you that that the value of the derivative does not exist at 2. I guess if I filled in one of those holes, it would exist, but that would be super weird. I think there's a way for that to happen, but I'd be really hard pressed to tell you what that would look like. Okay. Let's see. Melody. Did that answer your question? Feel free to pop something in there if you want something explained a little more. Okay. On what x intervals is f increasing, and on what intervals is it decreasing? Okay. Yeah, f prime of 4 doesn't f prime of 4 has a I guess it's a cusp. It looks like you could argue it's a corner. Okay. So let's talk about what happens. Let's say that we were trying to find the limit as h approaches 0. The limit like if we're using the definition of the derivative, the limit as h approaches 0, f of x plus h minus f of x over h for positive values of h. For the limit, this is the tangent line that's approached as h approaches 0 from the right. This is the tangent line that's approached as h approaches 0 from the left. And so the tangent lines are going to approach two different slopes. And so the limit itself does not exist. There is no line. I could zoom into this as much as I want, and there is no line that is going to approximate this function at that point. Yes, exactly. And so when we apply derivative logic to f prime, we use f double prime. If we want to know whether f prime is increasing or decreasing, we look at f double prime. If we want to know whether f prime is concave up or concave down, we look at f triple prime. We never do that, but you could. And so that window just keeps moving down. Okay. All right, so let's talk about increasing. And this is probably not the night to get into the argument about whether those intervals should be open or closed. Yeah. So here we look. So for question 1, we just look at the values of f. For question 2, now we actually need to look at whether prime is above or below the axis. So increasing. I want to be able to see the graph, so I'm going to just leave it here. Increasing for sure at if you're given a graph, then you can argue that it has a cusp. If you're not given a graph or corner, then if you're not given a graph, then you have to say something else. I just went one level deeper, just for the heck of it there, and also to emphasize that local linearity piece. Yeah, in the end, that's probably deeper than you would have to go. So f seems to be increasing where f prime is bigger than 0 for sure. It may also increase at single points where the derivative is 0. And so one. All right, can everyone see me? Yeah. Yeah, my webcam just kind of freaked out for a second. All right, so it looks like we have increasing intervals from 0 to 1. I don't have a lot of evidence for 0, but I feel comfortable with the idea it's probably increasing from 0 to 1 because 0 is the left endpoint, and then I know that did I write that right? Let's try that again. 1 to 2. Okay, and I'm not sure exactly what's happening at x equals 2. I'm not really sure whether the function actually ceases to exist there, which is a possibility. It could actually also have a jump discontinuity. I think the best thing to do is leave it open at 2. I don't like to use unions here. There's some Facebook discussion about whether you should use unions for these. There's a very technical set theory reason why it's slightly weird to say union for this case. So on what x intervals, it's okay to just give a list. I wouldn't use unions. And when you talk about the domain, you would use unions because the domain is one set. Okay. So just know that you don't have to use unions here. I feel comfortable closing it at 3 because if I stop that interval at 3, then everything before 3 will have been lower than f of 3. Okay. But if you leave it open, if your teacher wants you to leave it open, they don't generally grade that. I'm unsure whether they would take off for it. I have heard a table leader. All I'll say is this: I have heard a table leader talk about why it's wrong. Whether they would let it slide is another issue. I wouldn't. I would just list the intervals. There's no reason to tempt fate. If you forget, it's not the end of the world, I don't think. Yeah. So 2 to 3, and then nowhere else looks like, right? So let's talk about decreasing. Decreasing is the opposite. Okay. I'm comfortable including 3 in both endpoints, and this is something that I think drives teachers nuts. How can x equals 3 be both an increasing interval and a decreasing interval? And the answer is those two intervals are separate. There's a horizontal tangent at x equals 3. So it turns there. And so it's okay if you're looking at just the part to the right of where it turns, it will decrease. Don't a comma, Annika. I would write a comma. I would just make a list of the intervals. Okay, so I actually feel comfortable. I actually feel comfortable saying 3 to 8 without a break. The reason is that and if I were really writing this, I would actually have told you that the graph of f prime has a horizontal tangent at x equals 6, just so you knew that there was no ambiguity. But what I expect here is that at x equals 6, f shows a horizontal tangent, right? The function would be decreasing, have a horizontal tangent, and then just keep on decreasing, like negative x cubed. So I'm okay leaving 6 in the decreasing interval here. There's no reason to break it. Okay. So that's kind of what I'm expecting to see there. And I'm using a cubic as inspiration because I know that this is a parabola. Okay. It actually gets a little easier from here, maybe. Question 3, what values of x does f have a relative min? You don't know, you have no way of knowing where it could be without knowing a little bit more about f or the functions. Okay, but we know that f has a relative min at 1. Okay, so because I forgot it, I'm sorry. I'm going fast. Thank you. I think that's what you were trying to say. Someone told me that I forgot that interval. Okay. Because I got so obsessed with x equals 6 that I forgot about 0. I forgot about the first part. Sorry. I got so caught up in that. Okay, so relative min. If f is going from negative to positive and it crosses over 0, those are our textbook cases, right? X equals 1 is a critical point or a critical number. So I'm just let me just mark in here. Series critical number. X equals 2 is a critical number because the derivative doesn't exist there. It's not going to turn out to be anything because the derivative doesn't change signs. There's a critical number at 3, and there's a critical number at 6. Those are our only candidates for relative extremes. The only place where you get a relative min is at x equals 1 because the derivative goes from negative to positive. Oh, I think I'm doing that. Am I doing that backwards? Negative to positive. Yeah. Okay. So relative min at x equals 1. And similarly, I only see one relative max. All right. Cool. This is great. We're doing great. Hey, well, at least it was the internet, not the webcam. Okay. All right. Let's move on. So what values of x does f have a point of inflection? That would be where it changes concavity. Okay. So where are we? Thank you. Where are the points of inflection? Points of inflection. Okay. Okay. Cool. All right, this is a wild one. Okay, so x equals 6 for sure, right? Because f prime goes from increasing to decreasing, right? So f prime changes changes signs, right? So f double prime is greater than 0 here, and f double prime is less than 0 here. If you were to draw a tangent line to the tangent line, that would be f double prime. Okay, so x equals 6 for sure. Anybody see any others? X equals 4. Okay, same thing happens there. Even though f double prime doesn't exist, that is still a point of inflection because f is in the domain, or 4 is in the domain. Maybe 2. And my guess is that says f of x is defined for all real numbers. If you have a jump, it gets weird. So I'm not real comfortable with saying x equals 2. But if I said that f was continuous for all real numbers, then for sure it would have a point of inflection there. All right. So making a real broad question here. If f of 0 equals 4, then what is f of 1? Okay, so f of 1 is going to be f of 0 plus the integral from 0 to 1. I like using the accumulator for this. Then this is this area here is -1. So f of 1 is going to be equal to 3. And then by the same token, f of 2 is going to be equal to 4. It's 1/2 base height. Okay, this is a triangle. This is a 2x1 triangle. And so the area of that is going to be 1, but negative because the integral is the signed area. Okay, so there's a lot going on in this warm-up, and I've now spent 30 minutes on, which if you have me in class, you know that's the thing I like to do, spend 30 minutes on a warm-up. So, but this tells us pretty much all the things we need to do. And we're actually okay with the fact that it's not defined at 2 in this case, in case you're wondering. Fundamental theorem calculus is okay with a finite number of discontinuities. Okay, so let me go back to the slides real quick, because this is kind of the value. Like this is the value. This is what you came for. And then after that, I'm comfortable with as many examples as we feel like we have the energy for. So let me switch out of this. Okay. All right, so as soon as it loads, we focus down, you can see. All right, so when we use the graph of a derivative, this is the main thing here is to remember that the graph of f prime of x gives the value of the derivative. It's like a really souped up fancy table. So if f prime exists, f has to be differentiable. Yeah, that's pretty, because I've told you what f prime was, so there's no way it doesn't exist. You can bet that AP wants you to be able to tell the difference between f being differentiable and f prime being differentiable. Okay. where f prime is above the axis, f is certainly increasing because that means that the derivative is positive. Where f prime is below the axis, f is certainly decreasing. You may be asked to make a judgment about what happens as it crosses. If it bounces off, then you have to be really careful about that. Okay. The x-intercepts and discontinuities in f prime are your critical numbers for f. Okay. And f certainly has a point of inflection if f prime has a relative extremum. So f double prime of c might not exist. But if c is in the domain of f, then f might still have a point of inflection at x equals c. And that's a very common question. Like that seems to happen with points of inflection more so, that people think that the second derivative has to be 0 there. But the second derivative can be non-existent. And so that corner at x equals 4 in the warm-up shows that there could be a point of inflection. That's why I put it there. Okay. If f prime is undefined, f might have a point of inflection because you don't know if it's in the domain. There are some other things that you might not know about. Come on. That's a lot. There we go. All right. So this is the example we're going to take on next. So all of the different principles that we talked about apply to each of these problems. Okay. In the interest of time, I'm going to just give you a few seconds to kind of look them over and then start thinking about them yourself. I'm going to give you like a minute head start, but then I'm mainly going to start talking about them so that you can absorb some of the info. If you do really just want me to stop and be like, hey, like, give us a second here, or if you want to ask a question, I'm certainly happy for you to do that. Okay, this is I think there's value in both things. Okay. I may stop and ask you to think about one particular part, but I'm going to mostly present. Okay, but do take a look at this example. Yes, I will. I definitely honor that. So I'll let you guys talk about A and B. Then I'll remind you a little bit of C. And so while I don't have like 4 hours to show you every possible permutation, if you're looking at a graph of f prime, it helps you with a lot of things. So you'll be able to see that. Yes. I'd be quite comfortable including -2, but you can certainly, but that's the interval. Yeah, from -3 to -2. And it's decreased. Yeah. In Yarrow, you got one of them. I think there's another one. I want you to think about it. Because f prime exists, so f is continuous there for sure. And you're definitely going to see a point of inflection at x equals 0 because the derivative changes from the derivative of the derivative, the rate of change of f prime. And so one of the coolest shorthands for a point of inflection is going to be, does f prime have a relative extreme? Because if f prime has a relative extreme, it's definitely going from either negative to positive or positive to negative. And those are going to always be sound justifications for points of inflection. It's my video backwards. I think my video went backwards when I closed the app. I just switched it. Good, so all right, everyone good on those two? Does that help? I really like these examples are like, you'll see that a lot of them are cut from the same cloth. I want to show you some different cloths. So right, f prime, when you're arguing for POIs, f prime goes from increasing to decreasing. When you're arguing for relative extrema, f prime goes from positive to negative. An extreme of something is where it stops decreasing and starts increasing, or vice versa. If you were to actually graph this function, you would see that it would go from concave down, because the derivative is decreasing. So it goes from increasing to decreasing and goes concave down, and then it suddenly then it turns and goes concave up. Very smoothly, but it turns and goes concave up. And then down again. Yes, I will. Okay. I would love to show you a graph of this one. I just don't know if I have time to set it up. I'd love to show you the integrals on that one. That's a way I could argue that. X equals 0 is a POI. The justification is that f prime has a relative extreme at x equals 0. So f prime goes from decreasing to increasing. Good. All right, so let's go and talk about C. An equation for the line tangent to the graph of f at the point 0, 3. Let me switch to notebook. I'm going to write down the answers to the previous part in case you missed those. All right, that's probably the last time I'm going to switch out, so we don't keep having this vertigo thing going on here. All right. Okay. On what intervals, if any, is f increasing? It is okay to use the closed. I mean, for sure, it's okay at 2, because the increase will stop at 2. It'll have a horizontal tangent x equals 2. But if you're just considering the interval from -3 to 2, it's going to increase on that. And if f is defined on -3, it's certainly increasing at out of that point. So it's okay to include both endpoints there. But if you put the parentheses, it's okay. Okay. The shape of if f prime is a slope, I expect it to be a parabola. I don't know where the parabola will begin, but I expect it to be a parabola. And if the slope is downward, then it'll be a decrease. Then it'll be a downward opening parabola. And if the slope is upward, it'll be an upward parabola. Okay. Find the coordinate of each point of inflection. X equals 0 and x equals 2 because f prime has relative extrema. I can spell relative. Okay. For part C, the equation for the line tangent. Okay, so I like let me show something on you here. Besides the normal is slope intercept form. So y minus y1, you want to use y0. That's fine with me too. Is f prime. Let's see. Right, and so the equation of the tangent line is going to be at a known point. And so I actually know what the value of f prime of 0 is. The value of f prime of 0 here, x1, y1 is 0, 3. And f prime of 0, I can actually read off the graph. It's -2. And so I get y. I think it's easiest to write as point slope. But with my students, I teach BC, and with BC students, I also like to do the following. And there are 2 reasons I like to do that. The first is that it reminds them of Euler's method. The second is that it reminds them of Taylor polynomials. This is a first degree Taylor polynomial. If you're an AB, you don't need to know what that is, but they're cool. So this would be an alternative form of that. So I get y equals -2x plus 3. Yes, the slope is -2. So you could also write this as y. There are lots of ways you could write this as long as you write it using correct algebra. This is another way you could write that. Another way you could write this is y equals 3 minus 2x. That's what you get if you did it my way there, the third way. All of these ways are valid as long as you sequences and series. Once you get used to the idea that pretty much you're kind of asking yourself if everything's a geometric series like you learned in pre-cal, the series aren't so bad. It's when you start adding the x's, it just starts getting intricate. Okay. Part D. Part D is find f of -3 and f of 4. What you need to do is read carefully, right? You're told that f of 0 is 3. Okay. So for part D, f of -3 is equal to f of 0 plus the integral from 0 to -3 of f prime of x dx. Yes, I'm allowed to do that. I actually really like writing integrals backwards like this because it reminds me of what to do. I think this is my preference. Again, I think of this as the accumulator way of doing these kinds of problems. It's like if I know how f changes and I know where I started, then all I need to do is integrate to figure out where I end up. Okay, but you should recognize if this drives you crazy, you should recognize that this is just the fundamental theorem of calculus. If that weird man from Atlanta makes you sad with all the integrals, then this is just the fundamental theorem. That's the only way you're going to go. That's the only way you're going to do it. I have to add where I started in order to figure out where f of -3 is, because it might not start at 0. In this case, f of 0 is actually 3. The integral from 0 to -3 is the sum of two triangles. This triangle has area, and I need to be careful here. This triangle has area of, this is a 2 by 2. So this triangle is area of -2. That's the signed area. And this triangle has an area of 1/2. Okay. So let me break this down a little differently. I'm now going to subtract the integral from -3 to 0. And so this is 3 minus the sum of those signed areas. Okay, and so that's 7. I can do math. It's 5. 5 minus 1/2 is 9/2. Now, remember, if you are afraid of making a math error in that way, box the answer there. Don't simplify it. You don't need to. A reader has a scientific calculator and will type it in, and if your answer agrees with theirs, then you are good to go. Okay. Yeah. And then f of 4 is found the same way. And here, this is weird. This is like an SAT problem. Okay. So the area that I want, let me erase the stuff from before. The area that I want is this blue area here. Okay. And the blue area is equal to the area of the rectangle less the area of the semicircle. Okay. And then let's agree that it's going to be the negative of the geometric areas. Okay, so this is going to be -4 times 2 minus 1/2 of pi r squared. And the radius of this circle is also 2. Okay, so this is going to end up being 2 pi. I'm going to also distribute the negative in the same step. So this is 2 pi minus 8. And so this final answer is 3 plus 2 pi minus 8. Okay. I love these problems. I just love these problems. And you can see that a lot of the themes that we talked about from before are showing up here again. Use the graph to give you values of the derivative. And if the value of the derivative exists, it must be differentiable there. Right? Okay. How are we doing so far? You can't give me a thumbs up, thumbs down, but you can pop it in the chat. I got a few more. This is I just love this stuff. Okay, So let's talk about example number 2 that I brought. Okay. Yeah, I think thinking is good. Thinking is also hard. You'll remember the things you think about, but it's hard to think like for a sustained period of time. So I always like to try to make the most of it. Anyway, I hope this is all helpful. All right, so let's take a look at this example. The figure shows the graph of, it's another graph of f prime. Okay. Okay. You can see where notice how they're being very careful to tell you where the horizontal tangent lines are, and they're telling you the areas. So this is kind of like a little remix of the last problem, where you don't have to find any of the areas on your own, but you no longer have the benefit of being able to use you actually have to use the graph and the information given to you in of itself to find some of these values. Right. So I'm going to give you a 30-second head start here, and then I'm going to go through this one. Right. By the way, if you are in BC and you want to try alternate, I did pull a Brian Passwater. Yes. For those of you who are watching BC's AP Live, I did do that because I had to. That says x of f double prime of x. Okay, and this is actually FR4 from 2013. I fixed it in the slides, but didn't fix it in the notebook. Okay. Find all values of x on the open interval from 0 to xa for which the function f has a local minimum. And as a local minimum, the derivative goes from decreasing, the derivative goes from negative to positive. Okay, so that means that our critical numbers are here, here, and here. There are no sharp corners or not sharp corners. There are no discontinuities. Sorry, there are no discontinuities in the derivative. So those are our 3 candidates. The derivative has to change signs from negative to positive in order for it to be a local minimum. So the only local minimum is going to be at x equals 6, since f prime changes from negative to positive. And you technically need to also state that f is differentiable and thus continuous at x equals 6. Because if you don't have continuity of the critical number, you can't apply the first derivative test. Yes, many integration by parts problems can be done as tabular. I actually don't do tabular very much. Sorry. I'm willing to take a look at it if you have a question. But all right, determine this is my favorite one. This is a new thing. It's not a new thing, but determine the absolute minimum value of f on a closed interval. Okay, integration by parts cannot be an AB. So thank you, Lucky Stars. I guess I like integration by parts, but it gets intricate sometimes. All right, so determine the absolute minimum value of f. Now that is an extreme value theorem problem, right? F is continuous, so you can apply the EDT. So it must have an absolute min at an endpoint or critical number, right? Now, they haven't done you a lot of favors, but they did give you one starting point. They did tell you that f of 8 equals 4. So you can use the integral theorem in reverse to backtrack to the other function values. And so this is f of 6 must be -3. Because in order to get to f of 8 equals 4, and you accumulate an area of 7, that means you go from -3 to 4. of it. So I'm just going to subtract these areas. And by the way, the signed area is -3. So if I'm subtracting -3 from -3, this actually tells me that f of 4 is equal to 0. Okay, we got another, and finally we got another critical number at 1. So f of 1 must be -6. And that means f of 0 has to be -8. I could make a table of all of these, but since I've evaluated the function all the critical numbers, I know that the absolute minimum value is achieved. The absolute minimum is the y value. So it has an absolute minimum value of -8 at the endpoint. Okay. You only need to state what the absolute minimum value is. Technically, you don't need to say where it is. I could have gotten away without considering the critical numbers, which will clearly not be relative mins. I could have gotten away without considering 4 and 1. But I just like to. There's no reason to consider that intermediate work. Okay. All right. On what open intervals contained in the? Okay. Well, hang on. How am I getting the y values? All right, so I'm told that f of 8 equals 4. Okay, so this might help. I know that f of 6 is equal to f of 8 plus the inner. Let me actually reverse this, so I think that'll make it clear. F of 8 must be f of 6 plus the integral from 6 to 8 of f prime. And the integral from 6 to 8 of f prime of x is 7. And so I know that this is 4, and so So 4 is equal to f of 6 plus 7. And that tells me what f of 6 is. So that's how I get that f of 6 is -3. So hopefully that helps. Okay. On what open intervals is the graph of f both concave down and increasing? Okay, so that means that if f is concave down, f double prime is negative. And if f double prime is negative, that means that f prime is decreasing. But f prime should be greater than 0. Okay. And since we're not worried about, oh my goodness, what had just happened there? We're not worried about endpoints here because we're just looking at open intervals. Okay. So we're looking for intervals for which f prime is decreasing but still positive. Okay, I only see 2 of those kinds of intervals on here, and they look like 0, 1, and 3, and 0 to 1, and 3 to 4. Just again, list the intervals, and there's no need for a union. Okay, and so that's 0. Sorry about that. 0 to 1 and 3 to 4. And again, these are x intervals. Okay, so the fact that 3, 4 is a point on the graph, don't let that confuse you. Okay, so there are 2 different versions of D here. I like them both. I'll work them both very quickly. Okay, so if you're finding the slope of the line tangent to the graph of G at x equals 3, well, that's G prime of 3. Okay, now G prime of x, we have to chain rule this. So this is 3 f of x squared times f prime of x. Okay, so G prime of 3 is equal to 3 times f of 3 squared. That x equals 3, is that what I wanted to do? Okay, so I'm told that f of 3 is -5/2. Thank God, because if I didn't have that, I don't know how I would do this problem. Okay, then f prime of 3 is you're told is 4. And again, you can just stop. You don't have to simplify this. You would get 75. Because you would get 25 over 4 inside the squared, and then it would be 3 times 25 over 4 times 4. So you would get 75. But you can just stop here and have done. Okay. I wanted to do a little value add for your BC folks here. So those of you who are watching, I would do in this case, I would do u equals x and du equals dx. I'll let dv be f double prime of x dx. Therefore, v is f prime of x. So this integral evaluates. Okay, I'm going through this real quick. AB folks, just hold your breath. It'll be over in a second. Okay, so the integral from 6 to 8 of x f double prime of x dx is equal to the integral of x. It's not the integral. It's just the value of x f prime of x from 6 to 8 minus the integral of v du from 6 to 8. Okay, I'm almost done. Sorry, yeah. Okay, so I happen to know the values of f prime at 8 and 6. At 8, the value is 5. At 6, the value is 0. So I don't have to worry about that. And then this is going to be f of x. Oh, wait, no, well, I could do f of x from 8 to 6 and subtract. But honestly, the integral from 6 to 8, I know what that number is already. It's 7. And so this is, you could stop here. You don't need to try to simplify this. You could stop here. But that value will be 33. I love little twists on these kinds of problems. Okay. In the interest of time, you see I have example 3 here. I was going to engage in this lovely open-ended question. I'm just going to show you the context. Okay. So this is not a graph of f prime, right? On this next example, this is a graph of f. So what is this doing in this presentation? See if you can figure out what is f the derivative graph of. Okay. This is the key. And you have to write this on your paper somewhere. G prime of x is equal to f of x by the second, your book might probably calls it the second fundamental theorem of calculus. Okay. Your book calls it probably calls it second, some books call it the first fundamental theorem of calculus, whatever. Okay. But g prime of x is equal to f of x, because if you differentiate g of x, you apply the theorem, the derivative of 5 is 0. And if you apply the theorem directly into the integral, you get f of x. I get a lot of I should use this. I should use Rainbow more. I'm afraid it gets unreadable, but I should really use Rainbow more. People seem to like it. Okay. So now that you know this, now you can answer these questions. Okay. So the hardest part of part A is really g of 6. That's the hardest part. Okay, let's use Rainbow for at least a little bit longer. The hardest part is really g of 6. Because g of 6 is equal to 5. Well, okay, I lied. It's not that hard. I thought we would have to evaluate an integral. But I know what the integral from 6 to 6 of any function, well, assuming the function's integral, right? The integral from 6 to 6 has got to be 0. Therefore, the final answer is going to be 5 plus 0, which is 5. Okay. G prime of 6, then, is equal to f of 6. And f of 6 is equal to 3. And then g double prime of 6 is equal to f prime of 6. And you're told it has a horizontal tangent line. Therefore, f prime of 6 is 0. But this is a graph of a derivative in disguise. This is actually very common because they almost never just give you the graph of f. It could happen, but they almost never do because they want to know if you can reason going up and down. You can reason from f prime up to f using integration and down to f double prime. Therefore, make distinctions about whether f is concave in certain parts. Okay, so on what intervals is g decreasing? Okay, well, g is decreasing when g prime of x, which is really f of x, is less than 0. Okay, and I see 2 intervals for which that could be the case. That looks like the intervals -3 3, and it's differentiable on the closed interval. I feel comfortable using closed brackets here from 3 to 0, and then 12 to 15. Okay. They kind of, once they get past this first part, they kind of like pull the punches until you get to part D. And then C, on what intervals is the graph of G concave down? Well, G is concave down when G double prime of X equals F prime of X is less than 0, which means that F prime is decreasing. Okay. And it's decreasing on, therefore, it's from here to here. And so it's decreasing from 6 to 15. I know that the for part B, I know that the graph of G prime is the graph of F, and so I can read from the graph. If you want to know, I've stated the condition, and then I've used the graph. Now the reason it's closed brackets is because you can just consider those intervals in isolation. The endpoint on the right, 0, is going to definitely be lower than every point to the left of it. Okay. So this part, none of this is bad. Part D gets interesting because we've got a trapezoidal approximation of f of t, of the integral of f of t dt. And so we want to be very careful. Okay. Now you could use, you could draw them. You can actually draw what the trapezoids would be. Sometimes the trapezoids will be triangles. All right. And so the trapezoidal approximation using 6 subintervals of length t, they went easy on you here, but they figure like that's a lot riding on here. So you can actually draw the 6 trapezoids that would make up your trapezoidal approximation. You still need to compute it. And so this is going to be it's more writing than anything else. The integral from -3 to 15 of f of t dt is approximately f of -3 plus f of 0 over 2 times 3, 1/2 half the sum of the bases times the height. When G is concave down, you need G double prime. G double prime is the derivative of the derivative, and so that's the derivative of f, right? So G double prime is f prime. That's how I made that justification. So you need to know where f prime is decreasing. Okay. Let's see. And so you could basically the whole thing here. You might have learned in your book there's something called the trapezoid rule that works for this because the intervals are equal. This is very tedious, but if you just fill in the numbers, you'll be all right. And so the numbers happen to the numbers are -1, 0, 1, 3, 1, 0, -1. So it's -1 plus 0 over 2. And then you can actually factor out all the 3's. Plus 0 plus 1 over 2 plus 1 plus 3 over 2 plus 3 plus 1 over 2 plus 1 plus 0 over 2 plus 0 plus -1 over 2 all times 3. And I would just stop writing. I would just stop there. This is the right answer. There's no reason for you to get yourself into trouble by writing anymore. Just not. I would fill in the F's. I would be 100% comfortable with you stopping here. I wouldn't stop before that. once you get down to a numeric expression. You can leave like common unit circle values or trig values in. Like if you left cosine of pi over 2, they would accept it. Although there is a problem on here where if you don't know what the value of a unit circle function is, you will not get the problem right. So be warned. Okay, it is 10:10, and I think I love both of these problems. This problem is a rate in, rate out problem where the one of the rates is given as a graph, which is why I included it. So I'll just ask you guys: do you want me to work both of them, or do you want me to work one of them? I am okay either way. Okay. All right. So the key question here again. This is another graph of a graph of a rate. Now it's only a graph of a rate in. Okay, you're told that people move onto the ride at a rate of 800 people per hour. So the rate out is a constant 800. And so the net rate of people in line is going to be rate in minus rate out. Okay. So, but all we're talking about is how many people arrive at the ride between t equals 0. Oh, that's not a highlighter. T equals 0 and t equals 3. Okay. This is an integral of rate in only. Okay. So between t equals 0 and t equals 3, you can use the graph to reason about that. Okay, and so that's going to be, this is the number of arrivals. Okay, this is 2 trapezoids. So what I would do, for part A is I would do the integral from 0 to 3 of r of t dt, only the rate in, and that's going to be 1,000 plus 1,200 over 2 times 2. This is an unequal trapezoid, so it's 1,200 plus 800 over 2 times 1. Now this isn't an approximation. This is an equals. Okay, because it's not. Because I'm not just estimating. This is the rate. Okay. I am told that they do not really care if, like, they don't feel comfortable making the distinction between your handwriting an approx versus an equals. So how many people arrive at the ride between t equals 0 and t equals 3? That is 2,200. That's 1,100. That's these cancel. So that's 2,200 plus 1,000. 3,200 people. Okay. So that's part A. Part B. Okay, good. Okay. The AP Calc exam, once you get to the numbers, like, you could stop here. Especially if you don't have a calculator, you're not comfortable doing it, because if you write the wrong number, you get penalized. But if you write something that they can type into a scientific calculator and get the right number, you will not be penalized. Yeah. Sorry if I'm not being clear on that. Okay. Is the number of people waiting in line to get on the ride increasing or decreasing? So B. All right. So let's let L of T be the number of people in line. Then L prime of T is the rate in minus the rate out. Okay. And so is the number of people waiting in line to get on the ride increasing or decreasing between T of 2 and T of 3? Okay. So So this is increasing if L prime of t is bigger than 0. R prime of 2 is equal to 1200, and R prime of 3 is equal to 800. So L prime of t is bigger than, L prime of t is, and it's strictly decreasing. I'm trying to think of what I want to say here. L prime of t, so 0, I'll say it like this, 0 less than L prime of t less than 400 on 2t3. So the number of people must be increasing. I think that's the that's the pretty clean way of saying it. Yeah. All right, so for part C, at what time t is the line for the ride the longest? How many people are in line at that time? Okay. And so what I want to do here is basically, if it's defined over the whole interval, okay, then I need to check the line the longest. Okay, so I need to check the following. Okay, I need to make a few judgments about this one. Does everyone remember the stimulus? I'm starting to write here and getting past the stimulus. Okay, so basically I need the absolute maximum number of people in line, right? And so L prime of t RT minus 800 minus 400. There's only one critical number for L, and that is when, so L prime of 3 is equal to 0. Okay. So I could check the endpoints. But I happen to know that L is increasing on 0 to 3 and decreasing on 3 to 8. Yeah. Since L prime is bigger than 0 for 0t3. And L prime is less than 0 for 3 t8. Thus, L must be maximum at t equals 3. Yeah, we've lost the stimulus. So I'll do part D up here. Okay. So 3 is the break point, right? So this is the net rate out. So 3 is the break point. That's where it evens out. That's where it goes from more people are arriving to fewer people are arriving. In fact, that you can actually track the net number of arrivals by using, or the net number of people by doing an area like basically between these two functions. Okay. But here is where it goes from increasing to decreasing. Here is the critical number for people. Okay. So it wants to know how many people are in line at that time. So here, the net number of arrivals is above the line 800. Okay. So the easiest way to do that basically is to, you can make a couple of different arguments about this, but the basically what you're doing is the number of people in line at that time. There are 700 people in line at the start. So L of 3 is equal to L of 0 plus the integral from 0 to 3 of L prime of t dt. L of 0 is 700. Now, you could make a lot of arguments about 0 to 3, but the easiest way to do it is actually to take the number of arrivals from part A and subtract the number of departures. 800 people per hour. So that's the easiest way to do it. And so 3,900 minus 2,400 is 1,500 people. So this is part C. And then for part D, you want to know when an integral expression of R whose solution gives the earliest time t at which there is no longer a line for the ride. Okay. Well, the number of people is basically this. It's basically what we just did. So for part D, what you want to know is what value of t I want to know when there are 0 people in line. I'm changing the variable here. No one is actually going to complain at you if you don't change the variable, just so you know. But it says it's an integral expression of R. And so I need to go back to the definition I made for it. And so I could just use the fundamental theorem of calculus to answer that question. All right. So there it all is. There's a lot going on here. Okay. All right. Bonus problem. We are almost done here. And you'll notice that this is there's all kinds of integrals just floating around this problem. This is, I'm stealing a little bit of the FRQ thunder from next week, but I just really like this problem. So there's a continuous function. You're given a graph of f. Okay. Now this graph is there's an integral piece going on here, and so the reason that we're doing this is really part C. And so that there again is a place where you might be looking at the graph of a derivative hidden in plain sight. So we can do all parts of this. So let's do it part A. The integral from -6 to 5 of f of x dx. Here, I'm asked to make a judgment about a sub piece. So because 5 is further to the right than the -2, and I am not told what happens to the left of -2, but I am told the value of an integral. Okay, and so the value from -6 to -2, I can basically break this integral up at the -2. Okay, and this is what I want to know. Okay, I'm told that this is 7. This is the integral whose value I want to know, and I can evaluate the integral from -2 to 5 looking just at the information that's given. Okay, so these areas from -2 to 5, and so here's what I'm going to think here. Those areas are going to cancel out, so you get 1/2 minus 1/2, and then you get a -1/4 here, and then this area is going to cancel out here. And then you have a trapezoid. And that trapezoid has bases of 1 and 3. And then you have the area under a semicircle, or a quarter circle, excuse me. And so this quarter circle has side length 3, or radius 3, and that it's cut out of a square. So it's 9 minus 1/4 of pi times 3 squared. There's no rotation going on here. So these cancel, these cancel. This is 2. And so basically I get, I'm just, the work's all over the place, sorry. So I get 7 equals -6 to -2 f of x dx plus, so these cancel. So I got, it's 2 plus 9, which is 11, plus 11 minus 9/4 pi. And so the integral from -6 to -2 of f of x dx must be equal to 7 minus this, all this stuff. And you could simplify it if you wanted to, but please don't, unless you feel comfortable with doing it. There's no need for you to do this. This is a full point answer right here. Stop. Okay, so that's part A. Okay, part B. Oh, this is wild. Okay, it says evaluate this integral. So yeah, this, if you are thinking, hey, I got to write the function for this, what you could do is just reason about this question abstractly. You could break this up into several integrals. This is really like the first time I've seen the properties of definite integrals get used so much in a problem. This is pretty hardcore stuff here. So I can split up this integral in a lot of different ways, like that. And so this is going to be 2 times f of x. Hey, wait. Okay, well, I know how to do that. The integral of f prime has to be f. And so if you're looking at f prime, you go, oh my gosh, I don't know how to do that. Don't worry about it, it turns out, right? And then this is this ends up being 4x from 5 to 3. I already know it's 4 times 2, but there's no reason for you to worry about that. Okay, so this is 2 times f of 5 minus f of 3. Okay, and you would expect this to be the case, even though the area under f is positive, f prime is negative because the f is decreasing. So you would expect its integral from 3 to 5 to be negative. Okay, so that's not a mistake. And so this is plus 20 minus 12. Okay, I could have told you that. And so this is 2 times 0 minus 3 minus root 5. Here you have to use this value. Plus 8. And you could just leave everything. You could just substitute in the numbers and not add them together. No need to combine them. Okay. All right. Hang on there. We're getting there. All right. Part C. The function g is given by g of x is an integral. Oh, I really wish I'd picked some that had a chain rule for this x. I wish I had. I didn't. I wish I did. Oh well, too late. That's fine. Okay, so g prime of x, in this case, is equal to f of x. Okay, so finding the absolute maximum value of g, you're looking at this graph is the derivative of g. Okay, so you see there's a critical number here. There's a critical number here, right? And so we're looking at the endpoint. So this function, so f is differentiable. So f exists everywhere, and so g is differentiable everywhere. No, g, yeah, on this interval. So g must be continuous. Continuity also implies integrability, but that's, you'd be reasoning from the converse there. Okay, so g is -2 to 5. So absolute max at endpoint or relative max. Let's make a table. Okay, and I actually need g of x, not. Okay, so the table is going to have -2, -1, 1/2. Okay, and then 5. Okay, so g of x is the integral from -2 to x of f of t. Okay, so the integral from -2 to -2, that's 0. The integral from -2 to -1, that's positive 1/2. The integral from 2 to 1/2, that's going to be -1/4. And then you get all the rest of this. It looks like the absolute maximum is going to again be found in an endpoint. Okay, and I happen to know from which part, this part up here that I did before, I happen to know what the value of that integral is going to be. The value of that integral is going to be way larger than 1/2. It's going to be extremely large. If you wanted to, you could find it. It's basically all this stuff here. It's basically it's basically 11. And so it's going to be -1/4 plus 11 minus 9/4 pi. But you can see visually it's going to be the much larger number. So that's going to be that this value is going to be the largest value. I think that's actually a fairly challenging problem. Did I add a 1/4 where there shouldn't be one? Oh, it's from negative. I'm sorry. It's from that is all of that value. Sorry. So it should just be from 1 to 5. I'm sorry. There shouldn't be a -1/4 there. My bad. I got too excited. And then part D. That's wild. Any instincts about part D here? Just checking to see if you're all still listening. There's a limit. It looks very bad. What do you think might happen? Do we just try to plug it in? Okay. You know, by the way, that this function, if this, like, this is a composition of a bunch of continuous functions. Well, let's be clear. That might not be the case, but it looks like f prime is differentiable near 1. So near x equals 1, this is a composition of continuous functions. So we can just plug it in. Let's see what happens. And if something bad happens, we might get 0 over 0 or infinity over infinity. We might end up, probably not infinity over infinity. We might end up using, yes, L'Hospital's. But let's see what happens first. In this case, we might not get that. F prime of 1 is, it looks, F prime of 1, that the rise of this segment over the run, the rise is 4 and the run is 2. So it looks like the slope is 2. F of 1 is 1. Arctan x. Oh, there. I'm taking the limit. Sorry, I've already taken the limit. Okay, there are too many limits. You use candidacy, like if the integrals, you use the candidates test to find the min max of a function, no matter what. And that integral might be used to define the function. So all I'm doing is I'm using the candidates test on a function that happens to be an integral. Does that make sense? The underlying concept here is the candidates test. Okay. To me, this doesn't look like it's going to turn into 0, right? This is actually going to turn into 4 over 1 minus pi over 4. And since I got a number, that must be the value of the limit. which is really weird. It's like, I looked at that problem, I was like, for sure, this is a L'Hopital's. And then I plugged it in x equals 1. I'm like, it is not a L'Hopital's. The function has to be continuous to at the critical numbers to use the first derivative test. It has to be continuous over the whole interval to use the extreme value theorem, Annika. And so I'm trying to be careful to state the conditions that I'm using. That's a lot of, that looks like a lot of extra stuff, but it's necessary to justify the approaches that I'm using. Because if the function's not continuous at a critical number, you could redefine it to have any value you want. And therefore, I can't make any judgments about whether it's a relative min or max, or whether over the whole interval, I'm going to have relative mins and maxes that have just been pulled off of the function going all over places. Lila, they will never actually give you 0 times infinity on the AP exam. They only test 0 over 0 and infinity over infinity. But it would not be out of the question for them to give you infinity over infinity for like something that involved an exponential. I don't think that would be out of the question. You're just supposed to know the answer. Sorry. That was fun. That's fun. And so the knowledge of graphs, you not only have to think about graphs and the values of them, you may be asked to do integrals on them. You may be asked to do limits even. There's and tangent lines. There's all kinds of stuff that flow from the fact that you might be looking at the graph of the derivative of some function, which means that you might be able to find its values. If you find the area under the curve of a derivative function, that is going to tell you the difference in function values for the parent function, or not the parent function, but the original function, the function that you differentiated. So there's lots and lots of things and ways that you can use the graph of a derivative to solve FRQ problems on the AP exam, and this is a very broad swath of all of those different things. Okay. Questions? Oh, I see a question. Somebody asked a question. How can I download the presentation slides? If you are on the Fiveable site, then the presentation slides. If you're on the Fiveable site, the presentation slides are a link underneath the Crowdcast. I should have put them there. I hope that they're there. I feel like I put them there. If you don't see them, can you? But you can see them, right? I wonder if they're not downloadable. I wonder if they're not downloadable for a reason. Can you download or print them? Can you print them to a PDF or something? I can. And see, I'm able to edit them because I wrote them. So I can't tell you whether that's what's going on here or not. And I think that might be done on purpose. You can always screenshot every one of them. Sorry, we're trying not to. The slide deck's not too long, and all the FRQs are. Like the main thing is just the value add slide. Now I wish I had put something about the integral on there. So, but remember, we're talking about reasoning at a bunch of different levels. I think if I had to summarize, and I feel like you've come this far, I should wrap this up with a little bow. Yeah, I'm sorry I don't have a better answer for you. But basically, if you have a graph of f prime, you can reason about f. Does f increase or decrease? Right. I can use integrals to find a change in f values. Right. I can also reason down to values of f prime, f double prime. Is f concave up or down. And that asks the question, is f prime increasing or decreasing? Okay, and then I can use f prime, the relative extrema are candidate POIs. And then f prime, the x-intercepts, and I wrote this for, and discontinuities are, sorry, I should put that on the other spot. Candidate POI of f. And then clear, obviously, the big one is x-intercepts and discontinuities of f are candidate relative extrema. For discontinuities, beware if point is in domain of f. That's probably the very, very, very quick summary of everything we've done here and all the ways that you can use the graph of f prime. So anyhow, that went on for 40 minutes longer than expected. But I hope you got something out of it. Thanks for staying till the end. If you have any parting thoughts, I'd love to know, but I think we kind of should probably all go to sleep at some point today. I don't know where you guys are time zone wise. Here it is 10:40, so I should probably go to sleep. Yeah, well, thank you guys for being here. I wish you guys all the best.